Well, now we will use a polar-like coordinate system in 3 space. These are called cylindrical coordinates. Actually, this is not new. We already use cylindrical coordinates in many examples so far. But now we will look at it from the point of view of 3 dimensions. Okay. First of all, the argument is the following. Okay. We can characterize a point x, y, z. This is in Cartesian, of course, by using the 3 things in question in space. Okay, we have a point P. Okay. We drop a perpendicular to x, y, okay, and consider this length, which of course is the usual r that we know. Okay. And of course, we can measure the angle theta starting from the positive x-axis. And of course, we can use the z coordinate. So, if these 3 are given to us, then of course we have specified the point exactly. Well, this is obvious because the projection onto the xy plane, that's this point in question, is completely characterized by using polars. These are polars in plane. And if you add the z coordinate to it, you get your P. Well, this system, okay, r theta z, is called the cylindrical coordinate system in space. Okay. To understand what a system is, we look at what happens if we keep one of them constant, or rather, yes, one of them constant, the other are changing. So let us start with the z, of course. Say z is z0. This is, as usual, okay, this is a horizontal plane. As in XYZ system. Okay. So there's nothing new about it. When R is constant, what do we get now in 3 space? Okay. Now, R is the distance of the projected point on the xy plane, okay, from the origin, or in short, it's the distance of the point to the z-axis. Now, R is the distance, okay, to the z-axis. Or, when you project it on the xy plane, it's the usual polar R, which, of course, means the same thing as this argument. Okay, so if we consider all points whose distance to the z-axis is constant, certainly we end up with a cylinder. Here, the radius is R0. Okay. With radius R0. Hence, the name cylindrical coordinate system. Okay. So the circle in polar r, being constant, is now a cylinder. Okay. And what happens if theta is constant? Well, if theta is constant, then we end up, okay, namely this whole line in question. But, okay, we can go up and down. Namely, the polar theta gave us such a half line. Now, z is arbitrary, so we can go up and down, which means that we end up with a half plane, which is something like this. But of course, it goes down as well. So this is when theta is constant. So this is a half plane. Okay, it goes down, but it doesn't go to the left, to the other side, on the left. Namely, this does not extend this way, just on the theta 0 angle. If you add, of course, pi to it, you would get the other half of this plane. So these are the three basic things in a cylindrical system. Now, if we want to change our variables to these new variables, hence we are making a change of variable, okay, there are two ways you can do that. Now we know the official way, that is the rigorous way, by taking the Jacobian determinants and so on. We can do that, but we can do it geometrically as well. So, to use cylindrical coordinates, in triple integrals, we need to estimate the volume when, okay, r theta z change by, okay, delta r, delta theta, and delta z. Now, geometrically, this means the following. Okay, let us look at our XYZ system. So what we are doing, well, let us look at these two rays. Okay, why? Because this will be my delta theta. Okay. I will increase at some point by delta theta. In the meantime, okay, I will increase some r up to delta r. In other words, this distance here will be delta r. Okay? But at the same time, I will do it at the top by increasing z a little bit. So if I go up, okay, I will end up, okay, with the same type of argument, that is the same figure like this, okay, but with a thickness. That's a very bad picture. Let me redraw it. Okay. It will be the same thing at the bottom, perhaps like this. Let me exaggerate a little bit. But then you give it a thickness. the thickness is delta Z. So now this is a volume piece in space, and okay, throughout Z is increased by delta Z from some point on, and so on. Well, of course, this is a circle, okay, like this, just like these circles, but elevated, okay? And this is the distance between the radii of the two circles, so this is delta r distance, and this angle is still the same as this one. It is delta theta. Now, as we did before, we can regard this as a rectangular box when, okay, delta Z, delta theta, and delta R are very small. So we already know the distance delta R, the distance delta Z, but delta theta does not give this distance automatically, okay? But we did this before in polars, that is, this length was approximately r delta theta. So this would be r delta theta. In short, okay, delta V will be approximately, okay, delta Z, delta R, and r delta theta. This, of course, tells us that the volume into which we should decompose our S in space will be such box-like small solids. Okay. This tells us that the volume would be approximately this. So the triple integral over S of f dV, which is the limit of the sum of f pijk's times, now normally as volumes we would use rectangular boxes, but here, okay, we will use these pieces. Let me call this Sijk, which happens to be R delta Z, delta R, delta theta, or just it's the limit of f pijk star, which must be chosen, of course, from Sijk, and the volume will become R times, okay, the volume of the rectangular box in R theta Z. Because the sides are delta Z, delta R, and delta theta, and you multiply them. In other words, this is a triple integral, okay, of f of x, y, z, but you have to change them into cylindrical coordinates. Z is Z. You get an R for extra, and then you have dV in R theta Z system, and here S R theta Z system. Okay. So this is now the changed version to cylindrical system. Well, we expected this, of course, because in almost all of our examples where we used the polars after the iteration, we obtained an extra R coming. Well, that is the Jacobi. Of course, we can, okay, more seriously, or rather more formally, we can check, okay, as in doubles, the Jacobian, that is the determinant of, okay, let me just use this first, x, y, z with respect to r theta z. Okay, which is the determinant, okay, of derivatives of x with respect to r theta z, of y with respect to r theta z, and z with respect to r theta and z. And that determinant happens to be, let me rewrite that. Well, of course, x is r cosine theta again. Here I did not do those conversions, but they are the same as in polars. Okay, let me just say here x is r cosine theta, y is r sine theta, because these are the polar variables, z is z. Okay, so these become now cosine theta, okay, with respect to r, with respect to theta minus r sine theta, with respect to z, that is 0, y, similarly sine theta, okay, r cosine theta and 0, and z 0, 0, 1. And this determinant would be r cosine theta, okay, squared, minus r sine squared theta, which is just r. Okay. And it's positive, so we don't have anything to do for extra. So this tells us that also formally, indeed, this factor which comes in the cylindrical coordinate system is just r, but we expected that because this is not too different from the polar transformation. Okay. Okay, let us, well, we already had many examples of cylindrical coordinates, but we did not consider them as a new system in triple integrals. So some of these will be a review of the previous examples, but nevertheless, I will work on them. Let us see some examples. Okay, the question is change into iterated cylindrical coordinates. Okay, the first example is S is bounded by x squared plus y squared. It's 9. Z is 1 plus x squared plus y squared. And that is minus 1 minus x squared minus y squared. Okay. Now this is a straightforward example. You can directly see that. Firstly, we have a cylinder here, okay, of radius 3, which goes up and down. Okay. And we have two surfaces. Of course, this is always above this. This is the upper surface, this is the lower surface, but these surfaces are paraboloids. Okay, forget this one. This is a standard paraboloid. Okay. Adding one shifts it in the z direction by 1. So here we have a paraboloid. Where this point is 1, Remember, this was the 0 point. And at the bottom, we have the negative of this, so it's directly symmetric. And so here we have -1, and we have that is -1 minus x squared minus 1 squared. So you have a cylinder from top and the bottom. You chop it, okay? So it's a bounded cylinder-like thing, but the top and the bottom are not planes anymore. They are bottom of a paraboloid and the top of a paraboloid, but clearly this is always bigger than this one. And so we can use then the simpleness of this region, hence S is simple with respect to Z. Okay. So an integral of f dv would be, of course, in cylindrical coordinates, that is f r cosine theta, r sine theta, and z. And of course, we have r dz dr d theta. Okay. Well, it's simple with respect to z. This statement is valid in Cartesian as well as in cylindrical coordinate system. Okay. Because z is the same z. So you start from -1 minus r squared. Of course, we are in polar, that's cylindrical coordinate system. So it means polar. And it goes up to 1 plus r squared. These are for z. Now for r and theta, we look at the projection. The projection is, of course, this. It's a circle of radius 3, so 0 to 3 and 0 to 2 pi. And so now it's written in cylindrical iterated form. Okay. Well, a second example. This time S is bounded by let me be more explicit. Is bounded from below by, because there are more than one regions. Z is x squared plus y squared over 3, and by a sphere, okay, from above. Okay. We want to write it in cylindrical coordinate system. Well, first a rough sketch. We have the following then. Okay. We have a paraboloid and we have a sphere. Okay. Well, clearly, the paraboloid divides two solids from the sphere. The one above the paraboloid, that is this little piece here, and the rest. They are both bounded by both surfaces, so it must be clear which one is meant. Now, from below by the paraboloid, okay? So the paraboloid is the lower one, and the sphere is the upper one. This, of course, says that we have then the following case. So this is this. Okay. Below we have the paraboloid. Above we have the sphere as wanted. So this being S then, okay, in polar system, which of course is simple with respect to Z. This is simple with respect to Z. So, okay, an integral over S of f dv would be integral of f, okay, let me put this, r cosine theta, r sine theta, z, r dz dr d theta, and of course z starts from the paraboloid, goes up to the sphere, the upper sphere, so it starts from here, which of course is r squared over 3, okay, goes up to this one, which of course is 4 minus r squared under root. Okay. We take the positive one because we are in the upper hemisphere, and the rest, okay, the rest is over d. Well, d is clearly, from here, something like this. This is our d. And it is determined by the intersection curve of the two. So d is determined by the intersection curve of the two surfaces. So we equate them. Okay, r squared plus z squared is 4, and r squared is 3z. Okay. This, of course, tells us that we have z squared plus 3z minus 4 is 0, which means that the z is 1, or z is 16 minus 4 is 12, so it is minus 4. Okay. Clearly, this is not possible, since in S that is positive. So the intersection curve must be z equal to 1. Well, z equal to 1 means, in both cases, you can put z equal to 1. So replace z equal to 1 in the equations. Well, it doesn't matter. They give the same thing. Okay, if z is 1, it means r squared is 3 from here. If z is 1, it also says the same here. So we get r squared is 3, or r is square root of 3. Well, this is as expected, because it's a circle of radius something. So d is then a radius root 3 circle in the xy system. And therefore, we can now write down the whole thing in iterated cylindrical form. So this triple integral would be now, we already figured that out. I will not repeat the rest here. R dz dr d theta, and z from r squared over 3 up to root 4 minus r squared. And in the root 3 circle, r changes from 0 to root 3, and theta makes a complete revolution. So this is now written in iterated cylindrical coordinates. Okay. Yeah. Well, okay. So let me continue with the following example. Okay, let me start it on a new board, as in here. Well, our next example is where S is bounded by this curve, z is -1 and z is 1. Now, this is an important example, as we will see in a minute. First of all, the structure is quite simple. We have something here, and these are bounding it from above and below. Okay. What is this? Well, if you recall, it is a quadratic surface. We actually sketched it. Okay. But let me just enlighten you a little bit. Clearly, when z is 0, you have a circle of radius 1. Okay. When z is larger, negative or positive, you have symmetry in both. You have increasing circles increasing in diameter. And so, okay, in both cases, you have increasing diameters, and these curves were hyperbolas. Okay. So it was what is called a hyperboloid of one sheet. Okay. And you cut it from the top by z is 1, and from the bottom by z is -1. You close the top and the bottom, so you get a nice solid S. Okay. Now, we observe clearly the following. S is not a simple region or solid in z direction. Obviously, when you look in the z direction, okay, well, you enter somewhere here, okay, that is z equal to -1. You move, and then you go up. And you leave from the hyperboloid, but this part of the hyperboloid. Or, okay, if you move from here, you go up and leave from this point, well, which is a plane and a plane. So you start from a plane and you leave from a plane. But the story is not finished yet here. Well, we entered and then we left. We did not completely leave because, okay, actually this extends like this. Okay. So if you go further up, you again enter and you again leave. So you enter and leave 2 times here. You enter and leave once, but from different surfaces. So everything is in a mess here. Okay, so it's not simple at all. How can we divide S into pieces so that these become simple with respect to Z first? Well, if we start with the middle one, that is entering from Z equal to 1 and being inside and then leaving from Z equal to 1 requires that we must be within this boundary, that is this cylinder with radius 1. If you are in this cylinder with radius 1, okay, you enter from the lower part, you are always inside, and then you leave from the upper part. So it is one of the sections that we have to consider. What is left is, if you take the inside cylinder out, you have the surrounding part. The surrounding part still has this problem. So we have to separate them by cutting at half. In short, okay, we can decompose S as follows. Okay, S, remember, is this one. We can, okay, well, let me be a little bit more precise. That will be important for me. Okay. Now, I can take this cylinder out, call it S1. Now, in the rest, I can divide it from the bottom. Okay. But remember, this middle part is empty. When it is empty, I just have this part rotated. So when I look in this direction, if I'm in the middle, I never enter the solid. If I'm here, okay, I enter from the hyperboloid, leave from z equal to 1. So it's simple. Call this S2. And do the same thing for the lower one. Okay. Here, again, this part is empty. Okay. I'm just rotating the remaining part. So, if I'm in the center, I don't enter, and so don't leave. It's always emptiness. But on this part, I enter from z equal to -1 and leave from the hyperboloid. Okay, always. So this is a simple region. So I can take the union of these things. Okay. If I put them together, I will get S. Well, this says that I have to consider my integral as a triple integral over f. Okay. I want, of course, cylindrical because everything is in circles, or things circles, of course. And so I will have r dz dr d theta. This will be my integral over S1. Now, in S1, okay, z changes from -1 up to +1. These are the surfaces that I always have. In the meantime, my projection is the cylinder, hence at the projection I get a unit circle. A unit circle in polars is 0 to 1 and 0 to 2 pi. So this is the cylinder part. Plus, now for the S2 part, well, in S2, I enter from the hyperboloid and leave from z equal to 1. So I start from the hyperboloid, but the upper hyperboloid. Well, if I solve for z in my hyperboloid equation, I have x squared plus y squared minus 1 under the root. In polars, it means that I have here r squared minus 1. This is the upper branch or upper part of the hyperboloid. And then I leave from the upper plane, which is z equal to 1. And I do this, now looking from the top, look at the projection. The projection is here. I have nothing on top of this circle. Okay, it's empty at the middle. Okay, I have the larger circle, which is the top circle. The top circle is z equal to 1 and the hyperboloid. Looking at the equations, if z is 1 and I have the hyperboloid, it means that the radius is square root of 2. Namely, the hyperboloid r square is z squared plus 1, and z is 1, so r is square root of 2. Okay. I have this. Well, in polars, it's very easy to write this down. Okay, r starts from 0, but we are not inside, so we continue, and then we enter and leave from the first curve, r is 1, the last curve, r is square root of 2. So it starts from 1 to root 2. In the meantime, theta makes a full revolution here, so 0 to 2 pi again. And finally, over S3 case, okay, I wrote it this way. Now, in S3, Z changes, well, we enter from the bottom and leave from the hyperboloid in the picture. So, Z starts from -1, and we leave from the hyperboloid, but this is the lower part of the hyperboloid, which is Z is negative. So when we solve from the equation, we get the same thing, but the root must be negative now. So we have minus root r squared minus 1. Okay. This is the lower hyperboloid. Lower part of the hyperboloid. Apart from that, the rest is just an annulus again, as in this case. So I'm just writing it. So 1 to square root of 2, 0 to 2 pi. The projection does not change. So the sum of these three gives me integral over S. A word of caution. We have a symmetry in the hyperboloid. Clearly, if you cut it at z equal to 0, you have a symmetric part at the bottom. Okay? So can we combine these two symmetric parts? That's, can we combine S2 and S3 together by multiplying it by 2 or something? This is completely out of the question. Why? Because we don't know what F does there. We are not calculating the volume of S here. Remember, we have an F in the function, in the integral. So maybe F is 0 on top of this at the bottom, I mean in the lower part, but in the upper part, well, it is 2. Such F's exist. So then, symmetry here does not come into the picture at all. So, a warning. Since we have F in the integral, we are not calculating volume. To calculate volume, you need 1, but we don't know what F is. Okay, so triple integral over S2 of F and triple integral of S3 of F, okay, have nothing in common, even though S2 and S3 are symmetric. Okay, the reason we don't know what F is. Maybe on S2 F is 0, on S3 it is 1. Then we will get completely different answers. So such symmetries cannot be used directly in triple integrals unless you know that F is also symmetric. Then, of course, symmetry arguments can work in here. Well, this was a lengthy example, but of course we don't solve this problem this way. Why? Well, let us now look at it from a different point of view. Namely, instead of using Z first, now we are truly using cylindrical coordinates. Okay. We are taking R first. Then it's also simple with respect to R. Sorry, it is simple with respect to R. It was not with respect to Z. Now, S, so a note, S is simple with respect to R first. Why again? Because in this picture, as you can see, this is my S, okay. What is the positive R direction? How does R increase? Well, R is the distance from the Z-axis, vertically, I mean horizontally. So, okay, R increases horizontally, starting from the Z-axis. Now, R increases horizontally, starting from Z-axis. Okay, this was the same in two dimensions, of course. In polars, the polar R increased in all directions, starting from 0. But now we can have an elevation. We have a Z, so it becomes the distance from Z-axis. Well, we are already inside. We go, leave from the hyperboloid. And always from the hyperboloid. So, R changes from the surface, R is equal to 0, sorry, which is a surface that's a cylinder with radius 0, so it's the Z-axis, up to the second surface, which is the hyperboloid. So it changes between two nice surfaces. Well, so much, so good. Theta, of course, makes a complete revolution, and Z changes between -1 and 1. There are no fluctuations at the top or at the bottom. They are constants. So, okay, and R changes from the lower, the inner, let me say, surface, R equal to 0, to the outer surface, that is the hyperboloid. Okay, so this is simple with respect to R first. So let us do it. Thus, the triple integral over S of F dV would be F. We are using cylindrical coordinates, so R comes into the picture, but we use R first. It's not important how you choose the order after that, because, as we will see, they change between constants. So, R changes from, again, 0 to the hyperboloid. Well, the hyperboloid in cylindrical language becomes the following. Remember, it was x squared plus y squared equal to 1 plus z squared. Now, this was r squared. So it says that z is r squared minus 1 under the root, okay? Because r is positive, I took the positive. Sorry, I don't want that. I want r. Okay. R would be 1 plus z squared under root. And of course, it's positive because r is positive. It starts from 0, increases. And so, using it here, r starts from 0 up to square root of 1 plus z squared. In the meantime, z from -1 to 1 and theta 0 to 2 pi. And that's it. So, this argument in this node uses the true nature of the cylindrical coordinates rather than using polars, which was so in our previous examples. But here, we used the true nature of the cylindrical coordinate system. Well, in the next example, this will be a general one. We will go backwards. We will look backwards. We will sketch, okay, the following. Sketch as if triple integral over S is 0 to 2, 0 to root 2x minus x squared, and 0 to an a. It's a positive number. We have an f, and we have dz, dy, dx. Okay. Well, of course, there is no single s which this question determines, because the right side is a fixed number, and you can have infinitely many triple integrals which give that number. But the idea is to make use of the upper and lower bounds here and try to reconstruct the S that these suggest, even though the answer is not unique. Okay. So what does it all say? First of all, it says that z changes from 0 up to a positive number, so between two horizontal planes. So we have two horizontal planes at the bottom, at the top. In between, we must have a cylinder. Well, the cylinder is determined by this. So the question actually is find d in here. Clearly, for this, we need to determine what this means. This certainly means that x squared plus y squared is 2x, or x minus 1 squared, y squared is, which one? 1. Okay. Well, this is then, a circle of this form. So, y changed from 0 up to this circle. Well, y is 0 is the horizontal axis here. Okay. So we start from here and move up to this. This is what this suggests. This is the positive root, so y is positive, and so on. In the meantime, x changed from 0 up to 2, so this completely tells us that indeed we have the upper half circle. So this is d. Okay. Well, but this is d, but it's not the sides of our picture in our solid, because it should be a cylinder because there's no z in here. So it goes up and down. In other words, this is the projection. Okay? So in 3 dimensions, we have then, okay, this is x and this is y. We have a half circle like this with radius, it's a shifted one. So it's a half circle like this here. Okay, that's D. But it goes up and down. Okay, it's because there's no z in it. Okay. So you take this and move it up and down, but this tells us that it is bounded by 0 here, and it's bounded by, that is A here. So S is something like this. Well, this is supposed to be at the corner, and so on. These are vertical, the sides. At the bottom, you have z is 0. At the top, you have z is A. And the projection is the upper half circle. So indeed, because, we have this picture, and if we wrote an iterated form on this picture, we would precisely get that. So this answers the question. Okay. As a diversion, let us look at the same question, but for 0 to pi, 0 to a sine theta, 0 to root a squared minus r squared f r dz dr d theta. So the same question, meaning if this is equal to a triple integral over S, what is S? Okay. Well, of course, here, again, we can start from our D here. This D is where R changes and then theta changes. So this is an integral over D. Its signals in the xy system, okay, R changes from 0 up to a sine theta. Well, a sine theta, okay, would be just multiplied by R, because we always prefer R squared. It makes our job simpler. So we have x squared plus y squared is equal to a, right, r sine theta would be y. So this is a circle centered at zero and a over 2, and it has a radius of a over 2. In other words, it's the following. And the radius is a over 2. Okay. It's a shifted circle in here. So this says that radius, that is r, starts from the origin, moves in all directions up to this circle. So it moves up to this circle all the time. And it does this when theta changes from 0 to pi. Well, theta 0 is this one. And when theta increases up to pi, you have everything up to here. In short, this is D. Okay. So this is the projection on the xy system, xy plane. Well, it is bounded by z equal to 0. Okay. We have here a circle. Well, that's too fat. Something like this, with A here. And from the top, it's bounded by z equal to root a square minus r square. Well, to recognize what it is, squaring, it would mean that it's a sphere of radius A. So it's a sphere of radius A, so we get such a sphere. At the top. So all in all, what does the picture suggest? Everything happens on top of this D. This is the base. So this is the base, and on top of it, we have a sphere, okay, which is pretty large, but we don't care what happens, okay, far away. What happens on top of this small circle is just this sphere, and so we would have a projection, okay, but that projection would not, okay, how would that go? Let me see. It would, at this point, it will hit the z equal to 0. So before it, it does not hit z equal to 0. It stops somewhere. So we have here okay, part of the sphere, and everywhere else we have a vertical surface. Okay, because this part is the sphere part. It goes all around, but I mean, just on top of this part, it gives us something as like an ellipse, but this is not a planar part. Well, so this is RS. Okay. Well, at this point, all I would like to say is that cylindrical coordinates are indeed heavily dependent on the polars. They are generalizations of polars to 3 dimensions in a rather simple way. So it's not much particular to 3 coordinates, to 3-dimensional space. It's just a direct extension of the polars. Now, the next coordinate system we will discuss will be something which is particular to 3-coordinate system. It has no equivalent in plane.